Students, so here you are going to learn about the new type of code called as a Hamming code. Okay, so Hamming code is it is a type of NK linear block code. Okay, it's a type of NK linear block code in which it is a single error correcting and also it is a perfect code. So the general definition of a Hamming code is it is a single error correcting perfect code. Single error correcting means it is able to self correct. It is able to self correct if there is an error in one bit. That is what is called as a single error correcting code, right? That is t is equal to 1. That is the error correcting capability is equal to 1. That is called as a single error correcting code. That is if the receiver receives the code word and if there is an error in one of its bit, then the receiver is able to correct it by itself. That is called as a single error correcting code. Now, if that single error correcting code is a perfect code, then that code is called as a Hamming code. We all know what is a perfect code, right? We have seen that in the previous videos that perfect code actually means that if all the syndromes of the code, if all the syndromes has a unique error pattern, then that code is called as a perfect code. So a perfect code which is also a single error correcting code is how we define as the Hamming code. Okay, but this is just a very vague definition. If you want to actually define the Hamming code, you need to look at the equations first. Okay, so when you are going to write the equations, let's start with something that we already know. We all know for an NK linear block code, we all know what is N and we all know what is K, right? N is the number of output bits and K is the number of input bits. That is, N is the number of bits in the output code word. That is equal to N. Number of bits in the output code word is N, and we all know what is K. K is the number of input bits or the number of the message bits. Okay, so we all know what is N, we all know what is K. Okay, now one interesting fact is that we define the Hamming code using the number of parity bits. We all know that a single code word has see, if you look at the systematic code word, a single code word has part message and part parity, right? That is, it has a certain number of parity bits and it has a certain number of message bits. That is what is the total output code word consists of. Now, if the number of parity bits, which we define as M, okay, and if the number of parity bits is M is equal to N minus K, then that is how we define the Hamming code. That is, in this case, that is, the number of parity bits is exactly equal to the difference between the number of output bits minus and number of output bits and the number of input bits. This is how we define the Hamming code. That is, the equations to define the Hamming code is that first is M is equal to N minus K. Okay, where N, the number of output bits, is defined as 2 raised to M minus 1, and the K, the value of K, the number of input bits, is defined as 2 raised to M minus 1 minus M. Any code that defines or that satisfies these equations, these three equations, any code that satisfies these three equations can be used or is a Hamming code. So this is how we define the Hamming code. So the thing about this is that only a certain pair of numbers actually satisfies these three equations. That is one of the beautiful thing about it. So that's one of the interesting thing about it. That's only for a certain numbers. Like for example, okay, like suppose I have a message, okay, and my message is having 4 bits. So if a message is having 4 bits, if my message is having 4 bits, that means K is equal to 4. Okay. So in that case, I need to, if I want to encode this message using Hamming code, what code should I use for that? The code should I use for that is, we know that K is equal to 4, right? So I need to find the value of N. So in that case, what I'm going to do is, I already know that K is equal to 2 raised to M minus 1 minus M. Okay, so which means K is equal to 4. So 4 is equal to 2 raised to M minus 1 minus M. So which means you need to find the value of M so that you'll get the answer 4 over here. So what should be the value of M? Suppose if I put M is equal to 0, what will I get? I'll get 2 raised to 0 minus 1 minus 0, which is not equal to 4. How about if I put M is equal to 1? If I put m is equal to 1, I will get 2 raised to 1 minus 1 minus 1. Again, it is not equal to 4. What if I put m is equal to 2? If I put m is equal to 2, I will get 2 raised to 2. That is 4. 4 minus 1 minus 2. That's equal to 1. So that also not equal to 4. So how about if I put m is equal to 3? If I put m is equal to 3, that's interesting. If I put m is equal to 3, I will get 2 raised to 3, that is 8 minus 1 minus 3, which is equal to 4, which means if the number of input bit is 4, then the number of parity bits must be equal to 3. It must be equal to 3. Therefore, the number of output bits must be equal to 7, which means if you want to encode your message with a Hamming code, you should use a 7/4 linear block code. That is, a 7/4 is an example of a Hamming code, because 7/4 linear block code satisfies all these three equations. Here you see that m is equal to 7 minus 4, which is equal to 3, and we know n is equal to 2 raised to 3 minus 1, which is 8 minus 1, which is equal to 7, and here k is equal to, as we have seen over here, it is nothing but 2 raised to 3 minus 1 minus 3, which is equal to 4. So any set of numbers or pair of numbers that satisfies these three equations can be used as a Hamming code. Okay, let's take another example. Like for example, what example should I use? Okay, how about if I let's start with the output code word n. Okay, let's start with another number. So suppose if I want, we know that 2 raised to 5 is equal to 32, right? Okay, 2 raised to 5 is equal to 32. So that means n is equal to 2 raised to 5 minus 1. So that means n is equal to 31. Okay, and here m is equal to 5. M is equal to 5. So what is the value of k? The value of k is n minus m, right? N minus m, which is equal to 31 minus 5, which is equal to 26. So which means 31 comma 26 is another example of a Hamming code. So you see, this is how we define the Hamming code. A Hamming code is defined by these three set of equations. Okay, and one of the unique properties of a Hamming code is that it is a single error correcting code. Single error correcting code means what? It means that t is equal to 1. That is the error correcting capability of this code is equal to 1 bit. T is equal to 1. And if t is equal to 1, then we all know what is the value of the minimum distance of this code, right? We know the equation. The minimum distance of the code is actually equal to 2t plus 1, which is equal to 2 plus 1, which is equal to 3, which means this is also under the property of the Hamming code. That is, a Hamming code has a single error correcting capability, or in other words, the minimum distance of the code should be equal to, or should exactly be equal to 3. So any code that satisfies these properties is a Hamming code. This is how we define the general definition, the specific definition, the exact definition of a Hamming code. Okay. And one interesting thing about Hamming code, we all know that Hamming code can either be a systematic Hamming code or a non-systematic Hamming code. Okay, we all know what is the meaning of systematic, right? Systematic Hamming code means the message is also the part of the code word. We have seen that in the previous video. The message bits is also part of the output code word. It's also part of the output code. So that is called as a systematic. So we can define the systematic Hamming code is exactly the same as your systematic linear block code. That is, the concept is everything, the theory, the concept, everything related to that is exactly the same. That is, when you're going to design a systematic Hamming code, you are actually designing a systematic linear block code. That's the only difference. There is no much. That's the only thing. There's no much of anything new to study over here. See, for example, let's start with the letter H. Okay, we all know what is H, right? H is the parity check matrix. Okay, so we all know for a systematic linear block code, we represent H by using the equation P transpose I n minus k, where P is the parity generator matrix and I represents the identity matrix, and the number that you see here is the dimension of that identity matrix. This is how we write the H matrix, and we have seen that in the previous video. So for the Hamming code, in the case of a Hamming code, we define this as H is equal to Q I M. This is how we define the parity check matrix of a systematic Hamming code. Okay, this is the case of a systematic Hamming code. Okay, systematic Hamming code. Okay, this is in the case of a systematic Hamming code. So in a systematic Hamming code, here that is we define H is equal to QIM. If you look at these two, actually these two equations are one and the same. They both are one and the same. That is, Q is actually nothing but P transpose itself. Okay, here you write P transpose, here you write Q. That's all. Okay, and if you look over here, I have already told you that M is equal to N minus K. So writing I N minus K or writing IM, both of them are also same. Okay, so basically the same, but one unique property is that M is equal to N minus K. Okay, so that because of this, okay, since M is equal to N, that is since the number of parity bits is equal to N minus K, since the number of parity bits is equal to N minus K, I can tell you that all the columns of the H matrix, or the columns of the H matrix is the or are the non-zero M bits. That is the one of the unique property of the H matrix. That is, all the columns of the H matrix are the non-zero M bits. For example, here in this case, if I'm taking a 7-4, okay, if I'm using a 7-4 Hamming code, what is 7 minus 4? 7 minus 4 is 3. So which means, M is equal to 3, okay. So if M is equal to 3, it will be, what are those 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1. See, 1, 2, 3, 4, 5, 6, did I miss any number? Oh, I forgot 1, 1, 0, 1, 1, 1. Okay, yeah. So see, 1, 2, 3, 4, 5, 6, 7. See, all these are all the possible 3-bit numbers. Okay, and if you look over here, all the columns of the H matrix are the non-zero M bits. You see, which are the non-zero M bits? These are the non-zero M bits. 1, 2, 3, 4, 5, 6, 7. So 7. There are 7 non-zero M bits. 7, exactly 7 non-zero M bits, which means that which means, the other words, if you want to define H matrix, one example of H matrix will be looking like this. That is, H is equal to, okay, we all know that the last three will be a identity matrix. So I will write that 1 0 0 0 1 0 0 0 1, and the other matrix will be the remaining. So I have already used this, and I have already used this, and the remaining will be the remaining bits, the remaining M bits. Which what are those bits are? Let's start with this. That is 1 1 1, and we have 1 1 0, then we have 1 0 1, and we have 0 1 1. So this is one example of an H matrix. Okay, here if you look very carefully over here, if I can divide this into 2 parts, okay, and this part is what you call as IM. This part is what you call as IM. IM or IN minus K, both of them are same. Okay, and this part is what you call as the matrix Q. You can either call it Q, or just like previously, you can call it as P transpose. So this is how we represent the H matrix. Okay, and likewise you can also express the G matrix in exactly the similar form. We all know how we represent G matrix, right? Normally we use G matrix using the term that is IKP. Right? This is how we usually define the matrix of the generator matrix, right? That is IKP, where IK represents the identity matrix of dimension K by K, and P represents the parity generator matrix. So in the same way, you can define the generator matrix of a systematic Hamming code using the equation that is we have IK. What is K? K is actually, what is the value of K? 2 raised to m minus 1 minus m. So which means this is also I 2 raised to m minus 1 minus m, which is K itself. Okay, K itself. And what is P? P transpose is equal to Q. So what is P? P is nothing but Q transpose. P is nothing but Q transpose. So therefore, this is how we define the generator matrix of a NK Hamming code. okay, where m represents the number of parity bits. That is, the identity matrix is equal to 2 raised to m minus 1 minus m, which is equal to k itself. So this is ik. You can write this as ik. And q transpose is the means it's a transpose of the matrix q. So which means an example of G matrix can be defined as, first I will write the transpose of this matrix. So which is what the transpose of the matrix is represented as. Let me see. It is represented. So it will be 4 bits, right? It will be 4 bits. So it will become 1 1 1 0 1 1 0 1 and 0 1 1 1. Okay, this is the q transpose, and the identity matrix is 1 0 0. So 4 bit, right? Ik is equal to 4 bit, right? K is equal to 4. So I 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So this is how we define the systematic Hamming code, right? An example of a systematic Hamming code. So if you look very carefully over here, okay, this is nothing but q transpose, and this is nothing but ik or I 2 raised to m minus 1 minus m. Okay, so this is how we define the systematic Hamming code. Okay, so this is all. So basically you need to remember is that systematic Hamming code, only this much is able you need to remember. That is one of the important properties, that all the columns of the H matrix is used. All the columns of the H matrix are the non-zero m bits. That is excluding the first m bit, that is all 0. Excluding this, the remaining bits are what we are going to use as the columns of the H matrix. That's the only interesting features about this Hamming code. Okay. So far what we discussed is the systematic Hamming code. Okay, so what is the meaning of systematic code? Systematic code means in that output code word, the part of that output code word is exactly your message bits itself, and the remaining will be your parity bits. Okay, that is if you take an n bit code word, the part of them will be your message bits, and the rest of them will be your parity bits. Okay, for example, if you're taking a 7/4 linear block code, if you're taking a 7/4 Hamming code, okay, for a 7/4 Hamming code, what is the number of output bits? The number of output bits equal to 7. So let me mark it. So now 7 means this is 1 2 3 4 5 6 7. Okay, so if you take an example of a 7/4 Hamming code, a systematic. So if it is a systematic, okay, if it is systematic, then the first 4 bits will be your message bits. So for like example, let m1 m2 m3 m4 be your message bits. So in that case, the first 4 bits will be your message bits, that is m1 m2 m3 m4, and the last 3 will be your parity bits, that is p1 p2 p3. Okay, so we all know that if you want to have a 4-bit message, you need to have 3 parity bits. That is why you got 7, because 4 plus 3 is equal to 7. So this is how, that is the part of the output code word is your message itself, and the remaining will be your parity bit. This is how we define the systematic Hamming code. Now, what is the meaning of non-systematic Hamming code? For a non-systematic Hamming code, the message bits and the parity bits are all combined together, or they are all mixed together. Okay, so they are all mixed together, but they're not. So what? But just because they are mixed together does not mean that they are mixed randomly. They are not mixed randomly. That's one of the interesting thing about non-systematic Hamming code. That is, the position of the parity bits is at the power of 2. The position of the parity bits. Here you can see that the position of the parity bits is the last 3, right? In this example, that is, the first we have the message bits, then we have the parity bits, and they are all combined and kept a group together. That is a systematic. But in non-systematic, the message bits and the parity bits are all mixed. And if you ask how they are all mixed is, I'll use an example. That is, let's take a very long code word. Okay, here it is 7. Let me take a very long code word. Like how many code word? Let me see. Let me start from here. Okay, that is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 21. Okay, 21 is 21. So assume this is a very long code word, okay, 21 bit code word, okay, and I'm just taking a random example. So here we all know that 2 raised to 0 is equal to 1. What is 2 raised to 1 is equal to 2. 2 raised to 2 is equal to 4. 2 raised to 3 is equal to 8. 2 raised to 4 is equal to 16. 2 raised to 5 is equal to 32. Right? Okay. How many bits are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so here there are 21 code bits. Okay, so how to mark the position of the parity bits is simply mark the position as the power of 2. That is, what are the different power? There is the first bit as this one right here, the second bit, that is this one right here, the fourth bit, 1, 2, 3, 4, this is the fourth bit over here, the eighth bit, 1, 2, 3, 4, 5, 6, 7, 8, the eighth bit, and the 16th bit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is the 16th bit. Okay, so these positions that I have ticked over here, those positions will be containing the parity bits. That is how we mix the parity bits with the message bits. That is, those positions will be the parity bits and the remaining bits will be the message bits. That is how we construct the non-systematic Hamming code. So here in this example, here I have taken, I think this is a 21. This is the maximum space of the book. Okay, so here there are 21 bits. So which means if I use a 21 bits means here it will be, this is P1, this is P2, this is a fourth bit and that contains P3, and this is the eighth bit that will have P4, and this is the fifth bit and that will be containing P5, and it goes on. Okay, and it goes on, and the remaining will be your message bits. That is this, the message bits. So this should be M1, this should be M2, this should be M3, this is M4, this is M5, this is M6, this is M7, this is M8, this is M9, this is M10, this is M11, this is M12, M13, M14, M15, M16. See, so this is an example. This is M16. So this is a this is actually called as a, this is actually called as a 21,16 Hamming code. This is called as a 2116 Hamming code. Okay, see, because in 2116 they have 16 message bits and there are 5 parity bits. Okay, if you have a first 16 as your message bits and the remaining 5 bits as your parity bits, then that is a systematic Hamming code. Okay, but in non-systematic Hamming code, how it is done is the parity bits are the power of 2. They are the positions of the power of 2. So that is the first position. So 2 raised to 0 is equal to 1, 2 raised to 1 is equal to 2, 2 raised to 2 is equal to 4, 2 raised to 3 is equal to 8, 2 raised to 4 is 16, 2 raised to 5 is 32, and so on. So therefore, the first bit, the second bit, the fourth bit, the eighth bit, the 16th bit, and if there are any more space, the 32nd bit, then the 64th bit, like that, those positions will mark the positions of the parity bits. The remaining bits will be your message. So in our example, if you want to have a 7/4 systematic Hamming code, if you want a 7/4 systematic Hamming code, 1, 2, let me mark it, 1, 2, 3, 4, 5, 6, 7. Okay, 7. So we know there are 3 parity bits. So 3 parity bits means 2 raised to 0 is equal to 1, 2 raised to 1 is equal to 2, 2 raised to 2 is equal to 4. So the first bit, the second bit, and the fourth bit will be your parity bits, and the remaining will be your message bits. This is M1, this is M2, this is M3, this is M4. This is the 7/4 non-systematic Hamming code word. This is the 7/4 systematic Hamming code. See, you can see part message, part parity, but here the parity is at the positions of power of 2. So this is the non-systematic 7-4 Hamming code. This is a systematic 7-4 Hamming code. Okay, so this is how we define the non-systematic. Okay, and one interesting thing about non-systematic is that the construction of a non-systematic Hamming code is very easy. The non-systematic Hamming code. Okay, the construction of a non-systematic Hamming code is very easy. We start with the construction of H. Okay, so how to construct a non-systematic Hamming code is we start with the construction of the H matrix. So we start with, first let me write the steps. Step 1. Step 1, what we do is write the BCD. Write the BCD code of M bits from 1 to N. This is the first step. Very easy step. Write the BCD code of M bits from 1 to N. That's step 1. Step 2 is rearrange the sequences in reverse order. Rearrange the sequences in reverse order. And then step 3 is that find the transpose of the above matrix to get the H matrix. That's all. Very easy steps. And it's first you write the BCD code of M bits from 1 to N. Then you rearrange the sequence in reverse order, and that reverse or that sequence, that matrix is the H transpose. So if you want to find H, simply take its transpose. Let's take an example so that you'll understand how easy it will be. For example, okay, if you're taking in the case of a 7-4, let's take a 7-4 Hamming code. Okay, so 7-4 Hamming code means what is the value of M? M is equal to N minus K, which is equal to 3. So M is equal to 3. So I'm going to write the BCD code of 3 bits from 1 to 7. So what are those bits are? 1 to 7. It will be 1, 2, 3, 4, 5, 6, 7. Right? These are the numbers. BCD code 1 to 7. So numbers are 0, 0, 1, 0, 1, 0. This is 0, 1, 1. This is 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. See, so these are the BCD code of 3 bits from number 1 to 7. This is the first step. The second step is rearrange the sequence in reverse order. So I will write the reverse order of the sequence and I will get 001 will become 100, 010 will become 010, 011 becomes 110, 100 becomes 001, 101 is 101 itself, 110 is 011, 111 is 111 itself. So now I did step 2, that is I rearranged the sequence in reverse order, and this, according to step 3, this is nothing but H transpose. See, very easy. This is H transpose, which means H is nothing but the transpose of this, which means what? 1 0 1 0 1 0 1. You have 0 1 1 0 0 1 1, and here you have 0 0 0 1 1 1 1. This is the H transpose. See, so the construction of the H transpose is very easy. All you have to do is simply follow these 3 steps. Okay, that is you find the MCD, the BCD, binary coded decimal, or find the BCD of 3 of the M bits from and then you number it from 1 to N. Okay, and then you just simply reverse that sequence, reverse each and every sequences, and that matrix is actually the H transpose itself. So which means all you need to do is simply take its transpose and you will find the H matrix. See, That's it. So very easy. So this is how first for the construction of a non-systematic Hamming code, we start with the construction of the H matrix. Okay, not with the generator matrix. We start with the construction of the H matrix. Okay. So if we know what is, so we all know what is H matrix, right? We all know what is H transpose. We know what is H matrix. So we also, you already know this equation, that we know that VH transpose is equal to 0. We all know that VH transpose. So this is a non-systematic code word. So non-systematic means, how does this look like? P1, P2, M1, P3, M2, M3, M4. Okay. So this is the code word. This is the 7-bit code word, 7-bit non-systematic code word. And what is the value of the H transpose? Let me write that again over here. That is 10, well, the first one is 10, 10, 101. Okay, and you have 0, 1, 1, 0, 0, 1, 1, and the other one will be 3 zeros and 4 ones, 0, 0, 0, 1, 1, 1, 1. So we already learned that VH transpose, that is, if you multiply any code word with the H transpose, you will get 0. You should get 0. That is one of the important, that's one of the unique property of an NK linear block code. And the same thing is applying over here. So this is a non-systematic code. This is basically a non-systematic linear block code. So if I multiply this code word with my H transpose, I should get 0. So what does that mean? Which means that if I multiply, I will get P1. If I multiply this with the first column, I will get P1 plus P2 into 0 plus M1 plus P3 into 0 plus M2 plus M3 into 0 plus M4 equal to 0. Okay, this is one code word you got. And what is the other? If you multiply this with the second column, you will get P1 into 0 is 0. You will get P2 plus M1 plus the last two, M3 plus M4 equal to 0. And if I multiply this with the third column, I will get P3 plus the last 4, P3 plus M2 plus M3 plus M4 is equal to 0. So in that case, so this is the equation I got. We all know that in this Galois field of 2, there is no negative sign or anything like that, which means this plus actually represents, don't forget, this plus actually represents the XOR function. Okay, let me write the XOR function. Okay. So in that case, what is the equation for P1? The equation for P1 is M1 XOR M2 XOR M4. And P2, the equation for P2 is M1 XOR M3 XOR M4. And what is the equation for P3? The equation for P3 is M2 XOR M3 XOR M4. So now I have just showed you how to find the equation of the parity bits. Okay, the message bits will be the message itself. The parity bits you can find by using these equations. And how did I get these equations? Using this equation, that is VH transpose is equal to 0. So because VH transpose is equal to 0, each of these equations is equal to 0. Therefore, from here I can find my equations of the parity bits. Very simple. So from here I can find the equation. So how do I find the value of P1? You simply XOR the first message with the second message bit and the fourth message bit. How do you find the value of the second parity bit? You XOR the first message bit with the third message bit with the fourth message bit. How do you find the value of the third parity bit? You take the second message bit, XOR with the third message bit and XOR with the fourth message bit. That's how you find the third parity bit. See, so this is the equation for finding the parity bits, and you got this equation from here. VH transpose equal to 0. So that's another interesting thing you have learned. Okay, so in that case, again, now I'm going to ask, if you have really understood this, now you will be able to write the G matrix by yourself. It's very easy. try the G matrix by yourself. That is, let me say, we all know that the G matrix is, the dimension of the G matrix is K by N, right? Where K is equal to 4 and N is equal to 7. So K by N. So let me just, this is it, okay? And what will be those 7 bits? It will become, those 7 bits are P1, P2, M1, sorry, this is P3, M2, M3, M4. So how do I write my generator matrix? So simple. First I need to write P1. What is P1? This is P1. That is 1 0 1 1. 1 0 1 1. This is P1. What is P2? M1, M3, M4. M1, M3, M4. M1, M3, M4. What is M1? M1 is this one. This is itself is M1. Right? This itself is M1. What is P3? P3 is M2, M3, M4. And what is M2? Only M2. What is M3? Only M3. What is M4? Only M4. The first row, we have already studied that the first row represents the first message, the second row represents the second message, the third row represents the third message, and the fourth row represents the fourth message. That is, each of these, not messages, the code words, that is, each of these rows is also one of the code word. So that's how I written that. That is, I looked at the equations, I looked at the code word, and I marked the corresponding ones with respect to this message. That is, P1 will become 1 only if any one of them or all of them is 1. So that's why I marked M1, M2 and M3. P2 also, it is M1, M3, M4. So the first row, the third row and the fourth row. P3 is the second row, the M2 plus M3 plus M4, which means the second row, the third row and the fourth row. M1 represents the first row, M2 represents the second row, of course M3 represents the third row, and M4 represents the fourth row. You see? So now I have constructed the generator matrix. This is how we define. So it becomes very easy, right? This is how we define. So which means now I will construct each of these code words over here. Okay, I will construct each of these code words right now. So I will get this. So here you can see that V is equal to U into G, and you can see this is V represents the code word, and this is your code word, right? Non-systematic code word, and this is your message bit is 4 bits. This is 7, this is 4, and this is your generator matrix that you got just now. And so from here I constructed these code words. So you can see over here that there are 15 messages. Okay, I have taken 15 messages and I have constructed the code word for each of these messages, as you can see here, using this equation. That is, here you can see this is the output code word P1, P2, M1, P3, M2, M3, M4. This is how I represent the output code word. This is my input message U, that is M1, M2, M3, M4. And so here you can see here that this, how did I get the values of P1? By using this equation that I have got previously. That is, P1 is equal to M1 XOR M2 XOR M4. And how do I get the equation for P2? By using this equation, that is, P2 is equal to M1 XOR M3 XOR M4, and M1 is the same as the M1 over here. P3, how I got the equation for P3? Using this equation, that is M2 XOR M3 XOR M4. That's how I constructed the value of P3. And M2 is exactly the same as this M2, M3 is exactly the same as this M3, and M4 is exactly the same as this M4. So these are the code words of non-systematic 7/4 Hamming code. So this is how we create it. It all starts from creating the H matrix. And how we create the H matrix? First you write the BCD code of M bits. That is, you find the difference between the n minus k. You find the difference between n and k, that is m, and then you write the BCD code of m bits from numbers 1 to n, and then you just simply reverse it. That is the H transpose. Okay, and that's how we find the code. That's how we find H, and from H you can find this, and from this you can write the generator matrix. and then using this generator matrix you can simply construct all the code words. Okay, now one more interesting aspect about this non-systematic Hamming code is its error pattern and its syndrome. See, these are the syndromes, all the possible varieties of syndromes, right? You know that if all the syndromes is 0, that means there is no error takes place. So if syndrome is equal to 0 means then there is no error. Okay, but look at the remaining syndromes, that is when 001, 010, 011, 100, 101, 110, 111. So these are the remaining syndromes, okay, the remaining non-zero syndromes. Okay, and if you look at these syndromes and if you look at the error pattern is unique to the syndromes. And how unique it is that the position of the error is equivalent to the decimal number of its binary form. That's all. The position of the error bit is equivalent to the decimal number of its binary number. For example, 001. What is the decimal number of 001? It's 1. So therefore, the first bit is in error. If you get the syndrome 010, which means the second bit is in error because 010 represents the second bit. 010 is number 2, right? Binary number 2. 011 represents the binary number 3, which means the third bit is in error. 100 represents number 4, which means the fourth bit is in error. 101 is number 5, right? It's the binary equivalent of number 5, so which means the fifth bit is in error. 110 represents number 6, which means the sixth bit is in error. 111 represents the number 7, which means the seventh bit is in error. If all the syndromes are equal to 0, we don't need to write, it's understood. If all the syndromes are equal to 0, it means that all the error bits are 0, which means no error has taken place. That's a basic definition of syndrome, right? So that's another unique features about the NK Hamming code, that is the error pattern. The position of the error bit is equivalent to the decimal number of its binary format. So here you can say that S3, S2, S1, find the decimal number. All you have to do is simply find the decimal number of the syndrome, and that decimal number represents which bit is in error. Here you can see I have marked all the error bits in pink. See, so here 001, which means the number 1, which means the first bit is in error. In this error pattern, only the first bit is in error. Here only second bit. Here 011 is the code for number 3, so which means the third bit is in error. In this error pattern, only third bit is in error. So which means what it means is that, suppose, okay, if you are going to transmit, let me take an example. Which example do you want me to take? Let me take this one, okay. What is this? 0101010, okay. 0101010, okay. So let's take an example. I'm taking this example, 0101010, okay. So if I transmit this, okay, if the transmitter transmits this code word and the receiver had a mistake, instead of receiving this, the receiver accidentally received 01110, okay. So the transmitter transmitted the correct code word, but the receiver received the wrong code word, okay. And what did the receiver receive? The receiver received this 0111010, which means we know from looking at here, we know that the third bit is an error, okay. So what the receiver does is, the receiver is able to correct it. How it will be correcting it is that the receiver will find the syndrome of this. And when the receiver finds a syndrome, that is RH transpose, right? S is equal to RH transpose. So when the receiver finds the syndrome, the syndrome will become, the value of the syndrome will become 011. This will be the value of the syndrome. 011 will be the value of the syndrome. And what is 011? 011 is binary, it's the binary equivalent of 3. Right, it represents the binary equivalent of 3, which means that the third bit is in error. that is this bit. So what the receiver does, the receiver will reverse that bit. If it gets this is, here it is 1, so which means the correct bit must be 0, and like that the receiver will get the correct bit. This is the how this is the story goes. This is how the process is. So this is the working of the this is the working of the NK linear. I have explained the NK linear systematic and as well as non-systematic Hamming codes. Okay, the generation as well as its decoding. This is how we decode it.